Hello students, Dr. Dia here. We are going to finish our unit number 10 on chemical bonding. We have studied the valence bond theory that proposes that the way that chemical bonds are formed are by the overlap between the atomic orbitals of the adjoining atoms, or in some cases, by the formation of hybrid orbitals on the part of one of those atoms or both of them. But in any case, the idea is that electrons are shared in the overlapping regions of these orbitals. In our last lecture, we discussed that there are some flaws, some shortcomings in this theory that are hard to explain. For example, valence bond theory has a problem explaining molecules like nitrogen monoxide, where you don't have pairs of electrons. Secondly, valence bond theory is not good at explaining magnetic properties. I showed you that the molecule of oxygen should have all even numbers of electrons. Therefore, there should be no unpaired electron spins and the molecule should be diamagnetic. But I show you how if you pour liquefied oxygen through a magnet, it sticks to it. In other words, the molecule of O2 is paramagnetic. You can actually quantify these things by using a machine and equipment that is only sketched here. You are suspending your sample inside a tube from a balance. You approximate an electromagnet, you approach it to an electromagnet, and if the substance is paramagnetic, the electromagnet is going to draw in the substance because of the paramagnetic nature of it creating a magnetic field. You can then measure what is the weight being pulled up here in the balance and do some classical physics calculations where you can demonstrate how many unpaired electron spins there are. So with this in mind, let's propose a new theory. This is called the molecular orbital theory. In this theory, bonds are formed from the interaction of atomic orbitals to form molecular orbitals. The molecular orbitals are calculated by applying Schrodinger wave equation to the molecule instead of to individual atoms. In other words, in this treatment, the orbitals are going to be distributed throughout the whole molecule, and therefore the electrons are going to be delocalized. So rather than atomic or hybrid orbitals overlapping and the electrons being semi-localized in the region of that overlap, in this case, we are recalculating all of the orbitals, producing orbitals that are spread out throughout the molecule and therefore causing the electrons to be delocalized. So whereas in valence bond theory, the bonding electrons are perceived to be within the realm of the two atoms involved in the bonding, in molecular orbital or MO theory, the electrons are perceived as if they belong to the whole molecule. Now, let me give you kind of like an example of how this is done. You remember that we said in previous classes that when you combine waves, you have two possibilities. You have what is called constructive interference. You see it here on the left. The waves overlap in phase with each other, and so their amplitudes add up so that you get a wave that is much broader in amplitude than any one of the two you started with. This is called constructive interference. In the other case, when the waves are combined, they are out of phase with each other, and when you sum them, the amplitudes essentially cancel out, creating essentially a wave with no amplitude. Let's see if we could apply this to, for example, two atoms of hydrogen approaching each other. That's what we're going to look at here. Remember, the electron, the single electron in each atom is held in a 1s orbital. And I'm going to diagram here the wave function as a wave. So for example, look in the bottom picture here, all right? Notice what would happen if these two waves that are here on the left would combine with each other. Notice that if I were to trace this wave here on the left, I'm going to try to trace it here to the best of my ability. Comes there, and then it comes down, and then it comes up again. I'm keeping the wavelength, right? And then, and down, and again up. Now let's look at the one on the right. Notice that it's coming up. Let me see if I can use a different ink here better. Let's use a blue ink here for this one. So notice that what is happening is it comes up, then it comes down, then it goes up, then it goes down, and then it goes up. And so in other words, they are adding each other. They are experiencing what we call constructive interference here, right on the left side here. Now let's look at the case in the top here. Notice that in this case, this wave goes up here. Oh, I missed it. Then down here and down there like that. And whereas the other one, I'm going to do it in red now, would come up here, down there, up here, down again. Notice that at every point, they are out of phase with each other. And therefore, they experience what we are calling destructive interference. What happens is that, as you can see, I'm going to erase these lines that I made here. What you can see is that when you plot out the wave probability, the density probability, you can see where the one in the bottom gives us a region of dense probability right between the two atoms. And the other one essentially seems to project kind of outwards away from each other. These are the molecular orbitals. The one in the bottom, we call it a bonding molecular orbital. And the one on the top, we call it an anti-bonding molecular orbital. So let's see how that forms. Let's go back here to our diagrams. So let's say on the left, I have the 1s orbitals of each hydrogen approaching each other. Let's consider in the bottom, the constructive interference gives us a molecular orbital that distributes the probability density kind of right mostly between the two atoms along the same axis. On the top, you see destructive interference, where the probability density actually goes kind of away from each other. If we were to plot out the energy of these guys, we'd realize that what is happening here is that in the bottom case, you have the probability of the electrons being in locations, in regions around the molecule where they can experience the attractive force of both nuclei. Therefore, we would expect that to have lower energy. The one on the top, on the other hand, the electrons are kind of semi-pulled away from each other's nucleus and therefore not able to experience the full attraction force of that nucleus. And so we have a higher potential energy. We're going to call the one on the top the anti-bonding molecular orbital and the one on the bottom the bonding molecular orbital. Now, that doesn't mean that they don't work when they're anti-bonding. It just means that the bonding really is kind of opposed. It doesn't mean that they're not going to get occupied by electrons. Notice the way that we do the symbols here. For the bonding molecular orbital, we're going to use the letter sigma, similar to the sigma bonds of valence bond theory, because the electron distribution is along the axis between the two atoms. Notice that we also use a subscript 1s, which tells us, well, that was the source of the orbitals that got recalculated into this new wave function. For the anti-bonding molecular orbital, we also use the sigma, but we put a little superscript here, and we call this sigma star. So the sigma star 1s would be the anti-bonding molecular orbital. Now, if we look this on an energy diagram for hydrogen, you can see here on the left, each atom on the left and right of that diagram basically brought in one electron. So that means that our molecule must have those two electrons shown. Notice that the bonding molecular orbital has much lower energy than the anti-bonding one. Remember that when you generated these molecular orbitals, you can see them here on the right, the bonding sigma molecular orbital distributes density of the electron probability right there between the two electrons, between the two nuclei, I'm sorry. Whereas in the anti-bonding one, you have kind of like a tendency to kind of like move a little bit away, and you can see where there is a node in between the two lobes of that molecular orbital. So essentially, you can see that in terms of energy, the bonding molecular orbital has lower energy and therefore greater stability, not only than the anti-bonding one, but also it is lower energy and more stable than the atomic orbitals, the 1s orbitals of the atoms from which it was formed. On the other hand, the anti-bonding molecular orbital, the sigma 1s star here, has higher energy and lower stability, therefore, than the atomic orbitals from which it was formed. Now, let's see how we can use this theory, particularly for molecules that valence bond theory and Lewis theory would have a hard time explaining how they exist. So the criterion that we're going to apply is called the bond order. It's the difference between the number of electrons in bonding and anti-bonding orbitals. Now, the calculation goes like this. You add up the bonding electrons, in other words, electrons in bonding orbitals. You subtract the electrons in anti-bonding orbitals, and you divide that by 2. Several things. The bond order could be a fraction. Secondly, the higher the bond order, the stronger and shorter the bonds are because it represents a bigger difference between bonding and anti-bonding electrons. And if your calculation yields a bond order of 0, then that means that that bond would be unstable compared to the individual atoms, and therefore that bond will not form. That molecule is not going to exist. All right? So let's go here and play with an interesting species. Let's see if we could form diatomic lithium gas. Here is your energy diagrams. You can see on the left, you have one atom of lithium, atomic number 3. So 1s2, 2s1 configuration. And on the right, we have atom of lithium number 2. Now we're going to take all of those orbitals. We're going to recalculate them and produce these new molecular orbitals. All of the electrons have to show up in this new diagram. So that means 3 plus 3 equals 6. And we're going to fill these molecular orbitals the same way we filled the atomic ones, following the Aufbau principle of starting from the bottom and working our way up to higher energy levels and not putting more than 2 electrons per orbital. Okay, so let's fade out the atomic electrons and let's start filling up this molecular diagram. Okay, we're going to put 2 in there, and that fills up the sigma 1s, 2 in the sigma star 1s, and 2 in the sigma 2s. Remember, the subscript simply indicates the origin, the source, the atomic orbitals from where that molecular orbital was recalculated. And sigma represents molecular orbitals where the density of probability is distributed along the axis of the two atoms. So let's calculate the bond order. Remember, the formula is you're going to take the number of electrons in bonding orbitals minus those in anti-bonding orbitals and divide that by 2. So here we have in bonding orbitals, we have 2 in there and 2 in there, that's 4. And therefore there's 2 electrons in the anti-bonding orbital. 4 minus 2 divided by 2 equals 1. In other words, it's not 0. This is a stable molecule, and therefore we predict that in the gas phase, diatomic lithium could exist as a molecule. Let's look at some other interesting examples here. I'm going to do a sequence here between hydrogen and helium. And in some cases, I'm going to take electrons out. Again, bond order, number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding MOs divided by 2. So here are 4 examples. Let's go to the left here. This is dihydrogen plus. In other words, it's missing 1 electron. So when we make the diagram, you can see that you have 1 electron in sigma 1s and 0 in sigma star 1s. So that gives you a bond order of 1 minus 0 divided by 2, or 1/2. In other words, it's not 0. This could be a stable species. Hydrogen, of course, we already calculated. 2 electrons in sigma 1s minus 0 in sigma star divided by 2 gives you a bond order of 1, which in essence corresponds to our belief in valence bond theory that hydrogen made a diatomic molecule by forming a single covalent bond. In many ways, the bond order kind of corresponds a little bit to the idea of single versus double versus triple bonds. Notice a helium atom that has 3 instead of 4 electrons. It's an ion, positively charged, but it's a helium diatomic molecule. Again, bond order, 2 in sigma 1s minus 1 in sigma star divided by 2 gives you a bond order of 1/2, which means this species could exist. Now, when we get to helium, of course, we know that helium is a noble gas. It doesn't want to make molecules. And you can see here that when we put the 4 electrons in these proposed molecular orbitals, the bond order is 2 minus 2 divided by 2, which is 0. In other words, this would not be a stable molecule. Okay, now what happens when we recalculate or combine the wave functions of p orbitals? When we get to the second level, not only do we have 2s, but we have 2p. So let's do this. For the sake of illustration, since p orbitals are oriented along the x, y, and z axis, let's, for the sake of illustration, arbitrarily set up that, excuse me, the px orbitals are the ones that lie along the axis between the 2 atoms. And here you can see the lobed shapes of the 2px orbitals of the 2 atoms as they approach each other. Remember, in this case, we're not trying to create an overlap between those atomic orbitals. We are going to recalculate those. We're going to consider constructive interference, and we're going to consider destructive interference. When we do those recalculations, and understand when I say calculations, I mean it. This is a mathematical process where you recalculate wave functions using other parameters. These are the shapes of the molecular orbitals we generate. The bonding orbital, again, generates a region of high probability density between the 2 atoms. And so we call it a sigma orbital because the source was a 2p orbital. We call it sigma 2p. Notice that in the other case, for destructive interference, we generate anti-bonding orbitals. We call them sigma star 2p. Sigma because the electron density is still kind of spread out along the axis between the 2 atoms. However, in this case, the major regions of probability density are kind of facing away from the other atom, and there is a node right in between. We also put the subscript 2p to indicate that the source of this molecular orbitals set was the original 2p atomic orbitals. Now remember, there are 2 other types of 2p orbitals, 2pz and 2py. So let's consider the z-axis as the one that's kind of vertical, that's on the same plane as the screen. And again, let's produce orbitals from constructive and destructive interference. And what we find in this case is that the probability densities are distributed differently. They are located above and below the axis between the 2 atoms, generating nodes. For example, for the bonding one, which generates regions of probability above and below this center line here, you can see there's a big node in there. We call this, in analogy to what we did in valence bond theory, we call these pi molecular orbitals. Pi because the probability density is above and below the line between the atoms. In the case of the anti-bonding orbitals created by destructive interference, you can see like kind of like a butterfly shape, again, with a huge node in between and the majority of the probability density kind of facing away from the other atom. So higher energy, less stable. We call this the pi star 2p. Again, the 2p because it came from a 2pz orbital. We don't specify in this case that this particular set of orbitals came from the pz orbitals. We simply call them pi 2p and pi star 2p. And the reason is that there is a third set of orbitals, the 2py's, and let's consider this to represent orbitals lined up along the axis that goes through the screen, kind of like coming at us and going away from us. And again, you generate similar orbitals to what you got in the previous one, except they are kind of like at 90 degrees from the other ones. And again, you have a pi 2p and a pi star 2p. And the reason we don't specify whether it's y or z is because energetically, they have the same energies. So the pi 2p molecular orbitals have the same energy, whether they came from 2py or from 2pz. All right. So armed with this model, and again, I've given you a very simplified form of it, we can come up with how to build molecular orbital configurations. Several rules. Number one, the total number of molecular orbitals formed has to equal the number of atomic orbitals that were combined. Conservation of mass. Second, the more stable the bonding MO, the less stable the corresponding anti-bonding MO is going to be. That's a trend you're going to see. We're going to fill up the molecular orbitals from low to high energies, kind of like the same way we did with the Aufbau principle. Each molecular orbital can accommodate up to 2 electrons, similar to the application of the Pauli principle. When you're adding molecular electrons to MOs of the same energy, we're going to apply Hund's rule. In other words, first, we put electrons in separate orbitals before we start pairing them up. And finally, the number of electrons in the MOs is going to equal the sum of all the electrons on the bonding atoms. In other words, we're going to build these molecular orbital diagrams with all the electrons, not just the valence electrons. So I'm going to take you through an example. I'm going to do this on paper. So we're going to move over to our doc cam so that we can do that. All right, I apologize for my poor setup here, but unfortunately I ran out of white paper and didn't have time to go to the store to get some. So we're going to do it on a simple legal pad here. Okay, we're going to build the molecule of oxygen. Remember, that's the one that got us started on this. We realized that for some reason, the oxygen molecule with a even number of electrons is paramagnetic. The valence bond theory does not explain that, but let's see if the molecular orbital theory can do it. So what I have here is essentially the orbital diagram for 2 oxygen atoms. And remember, oxygen has an atomic number of, that's right, 8. So we're going to put our 8 electrons in here. 2 and 1s, 2 and 2s. And remember, as we fill up the 2p orbitals, we follow Hund's rule, and we end up having 1 completely occupied orbital. So let's do that on the other side also. Okay, remember in the molecular orbital theory, what we're going to do is we're going to generate a new set of molecular orbitals. So first we're going to take the 1s orbitals and we're going to recalculate a new set of orbitals here. And we're going to call this guy sigma 1s, and this one sigma star 1s. All right. For the 2s orbitals, we're going to do the same thing. We're going to recalculate a new set of molecular orbitals. Okay. And then we're going to say that this is going to be sigma 2s sigma star 2s. Now, how are we going to combine the 2p orbitals? Well, let's make some assumptions, okay? Let's make some assumptions. Assume that there is no mixing of s and p orbital wave functions, all right? Let's say that. Let's say that there's not going to be any mixing of those. In other words, when we make these combinations, it's S with S, P with P, and that's it. The other thing we're going to do is let's contrast two interesting set of orbitals. Let's contrast sigma star 2p, and let's contrast that with pi star 2p. I don't even remember the pictures, but the sigma star 2p, you had the two atoms here, and you had the little lobes here, and then the bigger lobes kind of facing away from each other. In the pi star 2p, here are the two atoms. I don't know if you remember, the orbitals look kind of like a butterfly like that. Please excuse my poor drawing skills here. So notice that in this case, it seems like the lobes in this case are kind of a little bit closer. So in other words, electrons in these molecular orbitals seem to be a little closer to the nucleus of the other atom than if they were in the, the higher density regions of these ones. And so we're going to say that the energy of the sigma star 2p is going to be higher than the energy of the pi star 2p. Okay, that's kind of like something we're going to come up with here. Now, also remember that when we built these pi and pi star 2p orbitals, right, they came actually from two of these original p orbitals. So we're going to have two of each. So with that in mind, here's the diagram we're going to propose, all right? We're going to say that the first thing we're going to have here is we're going to have a sigma 2p bonding orbital. And then from the combinations of two of the p orbitals, we're going to get a pi 2p. These would be bonding orbitals. And then the anti-bonding, as you saw, we decided that the pi star 2p are going to be lower in energy. So I'm going to draw them here. Pi star 2p. And then last but not least, I'm going to draw up here our sigma star 2p. And this is our molecular orbital diagram. Notice it's a little different than the ones we did for atomic orbitals when we did the Aufbau thing. Now remember, we're going to have to place all of these electrons in here. So we have 8 and 8. 16 electrons had to be shown here on this molecular orbital that I drew here. So let's start. Remember the Drake principle? You start from the bottom. Now we're here. Okay, sorry about that. So we're gonna put 16, right? So 2, 4, 6, 8, 10. Now remember, we have to first separate them, right? So we're gonna have 1, so it'll be 11, 12, 13, 14. I have 2 more, but I am faced now with 2 different orbitals, which means I need to keep them in separate molecular orbitals, right? Okay, so count again. We have 16 of them. Now what we need to do is establish, number 1, is this structure stable? Let's calculate the bond order. Remember that we said is the number of electrons in bonding orbitals. So that'll be 2, 4, 6, 8, 10 minus the number of electrons in anti-bonding orbitals. So that's 2, 4, 5, 6 divided by 2, and that equals 4 divided by 2 is 2. In other words, the molecule is stable. It has a bond order of 2, which kind of like sort of is analogous to the double bond we proposed when we did the Lewis structure. But most importantly than that, look at this. We have 2 unpaired spins in there. And that means that the molecule of oxygen is paramagnetic. That is something that we could not explain on the previous theory, remember? But in this one, we've been able to do it. Okay, let's look at a different molecule now, all right? Okay, I want us to look at a different molecule here. We're gonna try to build, using the same orbital diagram, a molecule of diatomic boron. Of course, boron is atomic number 5. So I have here on both sides here the atomic orbital electron configuration or the diagram for 5 electrons each. So remember, we have our molecular orbital diagram here, right, that we had done before, the same one that we did for oxygen. And in this case now, we're going to fill in not 16, but 2, 4, 5 times 2, 10 electrons, okay? So I'm going to start here with sigma 1s, that's 2, 4, 6, 8, and 10. Okay, all 10 are there. So let's do our analysis here. Number 1, let's calculate the bond order. Number of electrons in the bonding orbitals, 2, 4, 6, minus electrons in the anti-bonding orbitals, 2, 4, divided by 2, and that equals 6 minus 4 is 2, divided by 2 equals 1. In other words, according to this model, there could be a diatomic molecule of boron, and it would be stable. Now, we're going to ask ourselves, Is it diamagnetic or paramagnetic? Remember, the idea here is, are all the electrons paired up in their spin numbers, or are there any unpaired ones? And you can see here that according to this model, boron, diatomic, should be diamagnetic. It should not have a net magnetic field. So what scientists do is, just like we did with oxygen, let's test it out. Well, it turns out that B2 is paramagnetic. Oops. Does that mean the molecular orbital theory doesn't work? No, remember, that's not what it is. Remember that we made several assumptions. One of the big assumptions we made when we did the oxygen molecule was that we assumed there was no mixing of s and p orbitals. But what if in an atom like boron, which is less electronegative than oxygen, that exerts less kind of like, let's call it stress on neighboring electrons, maybe in this case you can have some mixing of s and p orbitals. So that's what scientists did. And what they found was that you could generate a different set of molecular orbitals. In other words, a different MO diagram for boron than you do for oxygen. So let's go and see how that works. Here on the right side, you see the diagram that we drew for oxygen, correct? Notice that the same diagram on the right applies to fluorine and neon. But if we allow for S and P mixing, you can see where you can generate a different set of orbitals than what you generated for our assumption of no S and P mixing. In particular, notice that in that case, the sigma 2p and the pi 2p molecular orbitals are flipped from what they were before. The model on the left explains the properties of diatomic molecules of boron, carbon, and nitrogen. Of course, of these three, the only one that we know really exists in nature is the N2, but the other ones can be produced in lab. Similarly, on the right side, we know that we're not going to see neon, diatomic neon, but we do see diatomic oxygen and fluorine. So notice that for the elements on the left side of the periodic table in this period to form diatomic molecules, they're going to use the molecular orbital diagram on the left where you allow for mixing of s and p orbitals to produce the molecular orbitals. For the elements on the right side, those that are farther right on that same period on the periodic table, you don't have the s and p mixing, and so you use the molecular orbital diagram on the right. So on the next chart, we can see what these diagrams are like. All right, so you can see the difference between the two groups here. When we build the charts, here we go all the way from lithium, which we did at first, all the way to fluorine. We're going to skip the neon here. These are all what we call homonuclear diatomic molecules. In other words, homonuclear because they have two elements of the same kind. Diatomic, there's two of them. And these are all second period elements. Again, remember when we draw that line, for the elements on the left, you can see where when you do the boron, because of the flipping of these orbitals, you do have those two electrons are unpaired, and as determined by experiments, B2 is paramagnetic. Of course, we already saw the case with oxygen where the molecular orbital diagram tells us that it is paramagnetic according to what we had seen already. Another thing that's interesting to notice here is the bond orders. Notice that in some cases, they match what we've known from Lewis theory. For example, nitrogen gives you a bond order of 3, which is kind of analogous to a triple bond. Oxygen to bond order of 2, analogous to a double bond. Fluorine, bond order of 1, analogous to a single covalent bond. Notice that the bond lengths also reflect the relationship between the bond order. So typically, the molecules that have the higher bond orders have shorter bonds, and the ones that have the smaller bond orders, more like a single covalent bond, they have the longer bond lengths. Also notice that the higher the bond order, also the greater the bond enthalpy. And you can see where, for example, nitrogen has a very high bond enthalpy. In other words, it takes a lot of energy to break up that nitrogen-nitrogen bond, which is interesting because many reactions that result in the production of nitrogen, in which case you would be releasing that amount of energy, are very explosive. So many forms of nitrogen compounds are used in the making of, explosive materials. And I'll leave it at that because I don't want to give you guys any bad ideas here. All right. Okay, so you can see where the molecular orbital theory is very good at explaining things that are not likely to be explained by the valence bond or Lewis theories, specifically the magnetic properties of these molecules. Of course, one of the features of this theory is that it proposes that the orbitals are delocalized. In other words, the orbitals themselves are not confined right between the two adjacent bonding atoms. They actually extend over several atoms, many times over many of them. For example, the compound benzene has the formula C6H6. If you try to do this structure, which is a ring of carbons, each carbon in an sp2 hybridized form with a single hydrogen attached to it, you would have to draw resonance structures for it. But in molecular orbital theory, what is proposed is that, as you see on the left, you have these orbitals that extend above and below the plane of that ring. That ring is actually a hexagon. And if you look at the electron densities, it's kind of like almost like there are 2 donuts of electron density right above the plane of that hexagon. In other words, all of these electrons are kind of like delocalized throughout the whole top and bottom of that hexagon. It's a totally delocalized set of electrons. You guys might remember this is the density diagram that proves that the electron density above and below the plane of that benzene molecule, that hexagon there. So it's kind of proof that you have this delocalized electron density above and below. You remember the carbonate ion. When we first did the Lewis structure of the carbonate ion, we found that we could draw 3 different resonance structures. And what we said was, well, this is a way of representing a structure that does not fit any one of those 3. It's kind of a blend of them, which, as you can imagine, is a little sketchy. But in this case, what we're going to propose is that the molecular orbital generated when we make the carbonate ion essentially produce these 2 areas of high electron density above and below the triangular plane of the carbon and oxygen atoms. And those electrons are completely delocalized in those regions. All right. So all very interesting stuff here. All right. And what I'd like to do is I'd like to conclude by addressing one of those molecules that we saw before where the Lewis structure did not work and where the valence bond theory had a hard time explaining the bonding. And that is the molecule of nitrogen monoxide. We're going to look at that on paper. Okay, I'm going to try to do a molecular orbital diagram for nitrogen monoxide. Once more, we're going to make some assumptions. Let's start off with nitrogen. Nitrogen is atomic number 7. So let's go ahead and fill in its atomic orbital diagram 2, 4. And remember that it's going to have the following Hund's rule. It's going to have the 3 2p electrons in separate orbitals. Oxygen, on the other hand, will have 8 electrons. So it'll be similar, except that when you reach the 2p subshell, you're going to have one of those orbitals is going to be filled. Now, in this case, we are combining 2 different atoms. And the question is, since nitrogen belongs to the left side of that second period and oxygen to the right side, the question is, which set of molecular orbitals we're going to use. So what we're going to say is that because oxygen is more electronegative, we're going to say that the molecular orbital diagram is going to be the one that oxygen follows. It's kind of like going to dominate here. Okay, it's going to set the rules. As a matter of fact, in some textbooks, what I've seen is that they consider that the oxygen atom would typically hold the orbitals a little closer. And so when you draw this diagram, sometimes they put the 1s orbital of oxygen and the 2s and the 2p's a little lower in energy than the ones in nitrogen. But I didn't want to distract the attention from the actual diagram itself. Okay, so remember that one of the things that we discussed before was that this 7 plus 8 gives me an odd number of electrons. And that was one of the problems with Lewis' theory that required all electrons to be paired, either as lone pairs or as bonding pairs. Well, let's do the diagram. We're going to put in here essentially 15 electrons, correct? 8 and 7. So let's start out with our molecular diagram here. 2, 4, 6, 8, 10, 12, 14, 15. So that is our molecular orbital diagram for the molecule of nitrogen monoxide. Let me block these off so we can get a more highlighted view of the molecular orbital diagram. So what we need to find out is, remember, in this case, the only issue we consider is the molecule stable? Does it give us a bond order that works? So let's see what the bond order is. I'm going to put it over here. So that's going to be electrons in bonding orbitals. 2, 4, 6, 8, 10 minus electrons in anti-bonding orbitals. 2, 4, 5 divided by 2 gives you 2.5 bond order. In other words, according to molecular orbital theory, this molecule is perfectly stable. It actually is very stable, 2.5. That's a very high bond order, which means it probably has a pretty high bond energy, right? And molecular orbital theory is not interested in saying, well, is it a single bond? It doesn't work that way. All it tells me is it works, and the electrons are delocalized over these collection of molecular orbitals. And it also predicts that nitrogen monoxide will be paramagnetic, right? I'm going to put that over here. Prediction is that NO is paramagnetic. And tell you what, I'm going to let you all look that up and see if it's true or not. Go look up NO and see if you can find out whether it's paramagnetic or diamagnetic. I'll let you work on that. The point is that both of the questions that prompted this whole inquiry here had to do with oxygen being paramagnetic, I mean diatomic oxygen, when Lewis and valence bond theory predicted it shouldn't be, and molecules like nitrogen monoxide with an odd number of electrons. How do you explain them? Molecular orbital theory can address those things. Now, molecular orbital theory is not good at explaining many of the shapes, the Vesper theory shapes that we encountered before. And so we find ourselves in a situation where we have two competing theories, both of which explain different aspects of bonding. And we might scratch our heads and ask, well, why can't we just have one? Well, remember, in the quantum world, there is an uncertainty principle. So we have to be comfortable with managing the uncertainty of not knowing exactly what is the nature of these bonding interactions. But anyway, I hope that cleared up a lot of stuff. And please read on the book more details. And we will now move on and begin the study of substances at the macroscopic level and utilize all these things we've learned at the atomic and molecular level to explain the properties of gases, liquids, and solids. So thanks for being with us. I see you soon.